Okay, so very good morning to all of you. So today I am going to introduce you with a new topic, and the name of that topic is DFA and NDFA. So DFA means Deterministic Finite Automata and NDFA stands for Non-Deterministic Finite Automata. So as we have already covered what finite automata is and why we are studying this topic during our TOC classes. So I told you that we are studying TOC. So it is all about theory of computation. Whatever computation is there around us. So what are the concepts behind that computation? How the computation starts and how it reaches to its final state. So I told you that your finite automata is actually a simplest machine to recognize the patterns. So this is just a quick recap of what we did already. So it needs some inputs. You pass the inputs to the automata, and during those inputs that it is getting, your automata, your machine is actually going through number of states, which are represented by Q, right? Q1, Q2, and so on, Qn. These are the states of automata. For instance, as I told you that let one state be the starting of the machine. Let the last state is the end point where your machine is turned off. So these two are the starting and ending states. But in between these states also there are number of states through which your machine passes. Okay. For example, if you are using washing machine, so your washing machine is in the state where it is spinning, right? It is in the mode where it is drying the clothes, right? It is in the mode where it is draining out all the water, the wastewater. So there are states of the machines, and it depends upon the input that you give, the button that you press, and what output that you are getting. You are getting that water will be drained out, you will get the dry clothes, right, to wear. And I told you that you represent your finite automata in the with the help of transition diagram. And I told you that this is the starting state and this is the last state. Okay, so Q naught, whenever there is a state to which an arrow is coming, right, that state is known as the initial state, and any state which has double circles around it, that state is known as the final state. Okay, now you give it an input. So here this is not a machine, so I am not going to press any button. So what my input will be, so to check, my input will be of the form of some string. Can you see here I have a string a b b a. So I will pass this string to it, right? And if by using this string my machine's state changes from the starting to the ending, it means this string is being accepted by my finite automata, by my machine. Okay, so for instance, I explained it that this is the string, right? So you are here at the starting state Q naught, and when you give a, this is the first input that you provide to it. When you give it a, the next state to which it reach is Q1. Next is B being processed. When you provide B to Q1, so it reached to Q2. After that, again, you have one more B, you will reach to Q3. The last A of the string will take you to Q4. Okay, so as this string is taking you all the way from the beginning state, the starting state, to the final state, it means this string is being accepted by your finite automata. So that's why you are getting this output accept, right? After that, here is an example where the rejection of the string will happen. So for instance, let's suppose that I have considered string A, B, and A, right? So again, I am in the starting state Q naught, and when A will be processed, this A when passed to Q naught will take me to Q1. Next, B will be processed, and B when passed to Q1 will take me to Q2. And the last one, when A will be processed, can you see this A is taking me to Q5. And after that, there is no string left to be processed. It means my final state is Q5, which is actually not the final state. The final state is Q4. Okay, so this string is not taking me from beginning state to the final state. So what output I will get? I will get the output that this string is being rejected by the finite automaton. Okay, there was another example that we did. This is a new automata I have considered, and the string is AAB. Okay, so if you are at Q0 and you provide it A, can you see it is taking you back to Q0 again? Next time again you are processing A, so it is again taking you back to Q0. The last one, which is B, it is taking you to Q1, which is the final state. And how you are able to see this is the final state? Because there are two double circles around it. So as this string is taking me all the way to final state, it means that this string is accepted, right? There is an example of rejection, BAB. So I am at Q0. When I process B, it will take me Q1. When I will process A, can you see from Q1, this A is taking you to Q2. Again, you are left with B. And from Q2, when you process B, it is taking you back to Q2 again, which is not the final state again. So it means your input is finished. There is nothing left to process. And this output is considered as rejected by this finite automaton. So if we discuss about the types of finite automata, so can you see here how many types of finite automata are there? So it can be classified into two types. Okay, so first one is right, and next one is non-deterministic finite automata, and sometimes it is termed as NDFA. Okay, short for NDFA, and sometimes we call it only NFA. Okay, so deterministic and non-deterministic. We have covered deterministic finite automata on the last class, but still I am going to give you a quick recap of it. So what is deterministic finite automata? Finite automata already cleared, but what is deterministic? Deterministic means something that you can determine, right? For instance, I'm giving you an example here, that suppose this is my state Q0 here, okay? And if I give it the first string B, so where my Q0 will go? If I am going to give Q0 the first input B, it will go to Q1. Okay, so on the basis of my current state and what input I am going to give it, I can determine my output state, that what my state will be. This is known as deterministic finite automaton. Okay, where on the basis of current state and on the basis of input you give it, you can determine, okay, what is going to be your next state, where your state will move from Q0 to next what state? Q1. I am sure that if Q0 will get B, obviously it will move to Q1. So deterministic means where the next state is already determined by the input that you give. Next example, suppose to Q1 I give A, right? So if to Q1 I pass A, so I am sure 100% that I will reach to Q2. Because from Q1, if A is given, it is taking me to Q2. So it means this state is already determined. There is only one state possible if you provide A to Q1. What is that state? That is Q2. Last example, suppose to Q2, if I give B. So if you give B to Q2, it is taking you back to Q2. It means your last state is also clear, it is also determined, and that's why it is known as deterministic automaton. So suppose you want to represent your transition function, so it is represented that this function is being represented here, right, sigma, and then you are at state Q0, which is the starting state, and when you give it A, you provide it A, it is taking you to the new state Q1. Okay, and again if you give Q0 B, Q0 is the initial state, you give it B, it will take you to Q5, right? Another example, you are at Q2 and you provide it B, it will take you to Q3. Okay, so this is the transition function table that I helped you the last day, that how you can create it. Okay, so here you write the transition function, that is lambda. Then A and B are the true, your input alphabets. So you write all the possible states here. Q0, Q1, Q2, Q3, Q4, and Q5. Can you see here in the first column? I have written all the states. Now from Q0, if A is provided to it, can you see here from Q0, if A is provided, where it is taking you to? It is taking you to Q1. Now to Q0, if B is provided, to Q0, if B is provided, it is taking you to Q5. So this is how, for the current state, for the input you provided, where it takes you, that is known as the transition table. And you can create it from the transition diagram or from the finite automata machine that is provided to you. So here I have one example for you, right? For DFA, Deterministic Finite Automaton. And what is DFA? DFA is that you have one current state. Okay, let me take you to the definition here. In DFA, for each input symbol, one can determine the state to which the machine will move. So suppose you are on a current state, and on the basis of the input symbol that you give to it, you can determine what will be the next state. Okay, and as you are able to determine the next state, it is called deterministic automaton, right? And as you know that it has a finite number of states, the states are countable. Some automatas have 5 states, some automatas have 3 states. As it has a finite number of states, that's why it is known as deterministic finite machine or deterministic finite automaton. Okay, so here is an example that I want you to check. Let's suppose Q, right? You know that your deterministic finite automata is represented by symbols. Okay, so first is Q. So Q means how many states it has. So previously I was representing states with Q0, Q1, Q2, but you can also represent your states with any other symbols. For example, you are representing them with A, B, and C. Can you see here? This is the A, this is B, and here C is missing. Okay, this is some problem with the diagram. So consider that here you have C. Okay, so instead of Q0, Q1, and Q2, now I am naming it A, B, and C. No issue. It is perfectly fine. Okay, so it has 3 states, A, B, and C. And now your input alphabet, which was previously made up of A and B, is now made up of 0 and 1. It means input is of the type 0 and 1 now. Okay, and here it is giving you a hint that your starting state will be A. It means this is your initial state and your final state is going to be C. So this is going to be your final state. Okay, so A is my initial state. How I can say that it is my initial state? When you see an arrow coming towards the state from nowhere, can you see it is coming from nowhere? So this is your starting state. And when you see that there are 2 circles around any state, this is your final state. So this C is your final state. And can you see, to all the states, the inputs are of the form 0 and 1. Okay, so if your A is getting input 0, it is taking you back to A. If your A is getting input 1, it is taking you to B. So your A is covered. I am repeating again, let's cover A. If A is getting input 0, it is taking back you to A. But your A, if is getting input 1, it is taking you to B. Now for B, if B is getting input 0, it is taking you to the final state, right? But if B, can you see here that if B is getting 0, it is taking you to the final state. But if B is getting 1, it is taking you back to A. Okay. Now in the final state C, if your C is getting 0, it is taking you back to B. If your C is getting 1, it is taking you back to C. Okay. So on the basis of what I have explained, this is the diagram. This is the transition table, that if A is getting 0, it is moving back to A. Can you see? If A is getting 0, it is moving back to A, right? But if A is getting 1, it is moving to B. If A is getting 1, it is moving to B. Again, next. If B is getting 0, it is moving to C. Can you see here? If B is getting 0, here B is getting 0, it is moving to C. But if B is getting 1, it is moving again back to A. B is getting 1, it is moving again back to A. Now my B is also covered. Let's talk about C. Now if C has 0, it is going to B. C has 0, it is going to B. But if C has 1, it is again going to C. Can you see? C, 1, it is again coming back to C. So just to summarize, if you talk about graphical representation, so this is a graphical representation. Can you see? A graph which has what? Which has edges, which has vertices, right? These are the edges, these are the vertices. So a DFA is represented by diagrams, right? And this is known as a state diagram. Okay, I'm telling you that this is a transition diagram, that this is your finite automata, that this is your finite machine. You can also say that it is a state diagram, because from one state on the basis of input, it is transiting from one state to another. There is a transition, there is a movement. Okay, now the vertices represent the states. These round vertices, right? These are represented as states in the graph, right? The arcs labeled with an input alphabet show the transitions, right? So this is an arc and it is labeled with some input alphabet and it represents the transitions. It is helping you to judge, to just finalize that from which state you are going to move to which next state. Okay, so how transition is happening and from which current state you are going to move to the next state. Okay, the initial state is denoted by an empty single incoming arc. Can you see? This is an empty single coming arc. Okay, empty means it is starting from nowhere. There is no vertex in before it. Okay, so it is coming from nowhere. That's why it is termed as empty single arc. Okay, and it is represented as your starting state, and the final state is indicated by double circles. So these are the double circles. So it represents that this is your final state. Okay, so after that, so this is one more topic that I want to cover here. We have done transition function. Okay, now you can also cover it in the form of extended transition function. Extended means I am not representing transition one input at a time. Okay, you remember here from current state only one input was given, like from Q2 only one input was given and you are moving to the new state, right? Now I have modified this function and it is now termed as extended function. Okay, now what do you mean by extended function? That we will cover here. So extended function is represented by this sigma and with the star on it. Okay, you have that number of states, which is okay. You have 1, 2, 3, 4, 5, 6 states. So your Q is representing how many states you have. Okay, and then this is represented as input alphabet. Okay, so your input alphabet is also modified and it is not just this summation sign, it is summation star now. Okay, so two things have changed. Your sigma is represented as sigma star because it is not a normal transition function, it is an extended, means it's improved version. Okay, and to extended transition function, states will always remain same. How you are making changes, how you are making it new. Okay, so how you are making it new, you are doing some changes in the input function, input alphabet, and undoubtedly it is again taking you to a new state. I'm repeating it again because it is represented as an extended transition function, so it is not sigma anymore, it is sigma star. States will remain same. From current state, it will take you to a new state. But the input alphabets will be somewhat changing now. That's why it is represented with the star. Okay, so how it is changing, I'm going to explain. So this is the transition diagram that we did first in the first class, the first transition diagram that we did. Now I'm going to help you with the extended transition function using this diagram. Okay, so now this transition function is starting from Q naught, obviously, because you always start from the first state, starting state. Okay, now instead of writing only A, can you see here, previously we were writing only one input symbol here, but now we are writing two input symbols. Okay, to Q naught, if I give A and B, where will it take me? What will be the next state? So I have to judge that from Q naught, if I will get A and then B, it will take me to Q2. So that's why Q2 is mentioned. I'm repeating again. Now input symbols are processed together and not one input at a time. So for example, if AB is given from Q naught, so how you represent? This is Q naught, first A, Q1, then B, then Q2. It means the final state will be Q. One more example. From Q naught, if A, B, B, A is given, where it is going to take you? So can you see this transition function star is getting input of the different type now. That's why how we are representing it? We are representing it with sigma star. Okay. So A, B, B, A. So from Q naught, A is taking you to Q1, B is taking you to Q2, B is taking you to Q3, and the last A is taking you to Q4. Okay, one more example. A, B, 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 A, A. So this is the input string. You are providing it to Q naught. So from Q naught, if it is taking you to Q1, B is given, it is taking you to Q2. Again, one more B, Q3. Again, one more B, Q5. And after that, how many A's you are getting from Q5, you will return again back to Q5. Okay, A, Q1, B, Q2, B, Q3, B, Q5, A, again back to Q5, A, again back to Q5. Okay, so the final state is going to be Q5. Okay. So this is explained here. So just let me know if this concept. So next we are going to cover non-deterministic automata, or you can call it non-deterministic finite automata. Okay, NDFA or NDA. That's on us. And it is actually the exact opposite of DFA, which is deterministic finite automata. So let's discuss it in more detail. Okay, so what is non-deterministic finite automata? So this is an automata I have. Okay, this is a state diagram I have. You can say this is a transition diagram I have. You can say, okay, this is a finite machine I have. You can say. Now we are going to check whether it is deterministic or non-deterministic. Okay, and if it is non-deterministic, how we people are going to guess it? Okay, I have one automata with me, I have one transition diagram with me. How I am going to figure out that this is deterministic or non-deterministic? So let's do it. Okay, so if the automata is in a state Q naught, now your automata is in state Q naught. Obviously, if you are starting a machine, so it is in the starting state now. Okay, on state, it is in the Q naught always, right? And the input symbol is 0. So to Q naught, if you give input symbol 0, what will be the next state? Can you see here? This is your starting state, and if you give it input symbol 0, what will be the next state? So here is an issue going to arise. Can you see here that if to Q naught you give 0, it is taking back you to Q naught also. But again, there is one more option here. Can you see here? If you give Q naught 0, it is also taking back you to Q1. So it means that for input 0, there are two chances of the next state. What are the two chances? Either for 0, you can come back to Q0, or for 0, you can also go back to Q1. Okay. So for one single input, your Q0 is showing you two transitions to two new states. One is back to Q0 again, that can be your next state. Other one is to Q1, that can be your next state. So this is written here clearly that if your automata is in state Q0 and the input symbol is 0, what will be the next state? So from the figure, it is clear that the next state will be either Q0, can you see, Q0, or it can be Q1 also. So thus, some moves of the machine cannot be determined uniquely by the input symbol. It means this input symbol is now confusing us. We are not able to determine that what will be the next fixed one state. We are confused now. We are confused between Q0 and Q1. Okay. So only input symbol and the present state is no more telling us what will be the next state. It is telling us two states. There are chances, go here or go there, which is not good. We want one final state, not two. Okay. So such machines are called non-deterministic automata or non-deterministic finite automata. Okay. And we are going to cover it thoroughly in the next slides. So let's discuss this NDFA definition in detail. Okay. So in NDFA, which is non-deterministic finite automata, for a particular input symbol, for any input, for example, here, for input 0, for any input symbol, the machine can move to any combination of the states in the machine. Okay. The machine can move to any combination of states. Okay. It can move to Q1 also. It can move to Q0 also, and maybe there are chances it can move to Q2. Okay. So if we have 3 states, okay, so from Q0 it can move to any states. Okay. So it can move to Q0, it can move to this, it can move to this, and so on. Okay. So in other words, the exact state, so this is the right definition actually, which is making your doubts clear. So in other words, the exact state to which the machine moves cannot be determined. You are not able to determine what will be the next one state. Okay. So suppose you people are starting from the college. Okay. So if you will get one auto rickshaw from outside the college and that is taking you to your home. Okay. You talk to that person who is driving that auto rickshaw. Okay. And he is telling you that he is actually going to the area near your home. So you are sure, you are ensured, okay, after riding this auto rickshaw, I will be able to reach my final destination, which is my home. Okay. But if that person will say, okay, I may go to your place, or I may go to some other place, or I may go to some other place, then you will be confused where it is going to take me. You are not determined. Your final state is not determined. Okay. But you want it to be determined. You want that it should be determined prior to your ride. Okay. Otherwise, everything will be confusing. You will be tense. You will be afraid. This is one example that I can give, that the exact state to which the machine moves cannot be determined. It is called non-deterministic automata. Okay. And why we call it finite, non-deterministic finite automata? Because states are always finite. States are always countable. There are 5 states in some transition diagram. There are 6 states. There are 3 states. Okay. So as the states are countable, they are finite in number. That's why it is called non-deterministic finite machine. Okay. Why non-deterministic? Because the next state you can't determine. Why finite you call it? Because the number of states are always finite. You can count them. Okay. And as it is a machine, it is a concept of machine. We call it machine. And or you can say that machines are automatic. You can call them automatons. So now let's do a formal definition. As in case of deterministic finite automata, I told you that it has Q. I'm talking about deterministic. In case of deterministic finite automata, I told you it has Q, it has this sigma, sorry, summation, this sigma, this Q0, this F. Similarly, your your NDFA also has these 5 tuples, these 5 symbols. Okay, what symbols? The same like your DFA. Q, then summation sign, then sigma, then Q naught, then F. Then how it is different than your DFA? Let's discuss how it is different. So Q is again a finite set of states. Good. If your transition diagram is like this, so what will be your Q? It will be a set of Q0, Q1, Q2. Okay, so Q represents how many states you have. So it is perfectly fine. So Q is giving me how many states I have in my NDFA. After that, sigma is a finite set of symbols called the alphabets. It is also same like your DFA. That for this, what is going to be your sigma? 0 and 1, because your inputs are made up of 0 and 1s only. Sigma. Okay, here sigma is different and it is the only thing that is making your NDFA different from DFA. So what is sigma? It is the transition function, undoubtedly. But here sigma represents that from current state Q, if any input alphabet is given to you, it is taking you to, there is one correction here. I'm not able to put it in the power. It is 2 raised to power Q. Okay, consider it as 2 raised to power Q. Okay, so if there are 3 states, it means what will be the next state? The chances are 2 raised to power 3. You can move to 9 different combinations. Next is not determined. Previously in DFA, it is only Q. It means next state is determined. But here it is a, you can say permutation, chances. There are 2 raised to power number of states chances. 2 raised to power, if the states are 2, there are 4 states to which it can move. If it is 2, if there are 3 states total in your finite automata, the next state can be any between 2 raised to power 3 means there are 8 states to which it can move. Okay, it means next state is not determined. Okay, here the power set of Q, that is 2 raised to power Q, has been taken because in case of NDFA, from a state transition can occur to any combination of next Q states. Jitni bhi states hain, you can move to that. Q naught is the initial state. This is the same as our DFA, and F is the set of final states. This is also same as the DFA. Only the difference is in the transition function, that the final state can be so many. There are combination of 2 raised to power Q, where Q are how many states you have currently. So your non-deterministic finite acceptor or automata or machine, whatever you call it. Okay, so M represents machine, and how you represent it? You represent it with Q, the number of states, the input alphabet, the transition function, the initial state, and the final state. All the 4 things, these 2 and these 2, all these are same like DFA. Only the difference is in the transition function. Means where to go. Transition means where to go from current state to another state. That is the only difference. So in case of NDFA, it is represented as Q into sigma, summation 2 raised to power Q. Whereas in case of DFA, how it is represented? It is represented as sigma Q into summation goes to Q. This is the only difference. And you know that the definition difference is also there. I have given you state diagram difference also. So I guess that everything is now clear to all of you. So graphical representation of an NDFA, it is same as DFA. You can see that there is no difference. The state diagrams are same. It is represented by the edges or vertices and the edges. Okay, it is represented by state diagram. Vertices represent the states. Arcs labeled with an input alphabet show the transition. Okay, the initial state is denoted by an empty single incoming arc, and the final state is indicated by the double circles. So everything is same, right? The only difference is that some arcs, can you see, some arcs represent the same input alphabet more than one time. Can you see? From Q0, 0 is represented 2 times. Okay, from Q1, 1 is represented 2 times. It means the outputs are not fixed. Otherwise, the state diagrams with which you have represented DFA is the same way you are using to represent your NDFA. Okay, so let's do one example here. This is the last thing that we are going to cover today. So suppose I want to process, so these are my states. How many states my NDFA has? This is NDFA. Okay, it has Q0, which is the starting state. It has Q1, Q2, Q3, and then there is Q4, which is the final state. Okay, so starting state is Q0, final state is Q4, and the input alphabet is 0 and 1. It means all the inputs are of the form 0 and 1. Okay, now suppose the string that I was given to process is 0, 1, 0, 0. Okay, which string I was given 0, 1, 0, 0. Okay, so let's do it. Okay, so you are at Q0, you are at the initial state. Okay, so the first thing that comes is, what is the first thing that comes? It is 0. Okay, so if from Q0 0 comes, from Q0 0 comes, where it is going to take you? It can take you back to Q0. Can you see? From Q0, if 0 comes, it can take you back to Q0. This is one scenario. But from Q0, if 0 comes, it can also take you to Q3. Can you see here? From Q0, 0 can take you to Q0 also. And from Q0, 0 can take you to Q3 also. So there are two states that can be reached if Q0 is given input 0, 0. Okay. So 0 is processed. After that, what you have to process? You have to process 1. Next one is 1. Okay. So if you have reached here, suppose from Q0 using 0, I have reached at Q3. I have reached at Q3. Now I want to process Q1. I want to process 1 here. But can you see from Q3 there is no 1 coming out? From Q3 there is no 1 coming out. So that's why this is discarded here. So you are reaching from Q0 to 0 Q0, and for 1 you are reaching to from Q0 for 1 you are reaching to Q1. From Q0 for 1 you are reaching to Q1, and from Q0 to for 1 you can also again come back to Q0. I'm repeating it again. I know it's a bit difficult to understand it from a distance. So again I'm repeating. So the string that we are going to process is 0, 1, 0, 0. And this is the transition diagram that we have. Okay. So from Q0, if 0 is processed, from Q0, if 0 is processed, one chances you can come back to Q0. Other chances you can go to Q3. So can you see here? Two chances are there, Q0 or Q3. Okay. So after this, the next one is 1. Okay. So from Q3, if you give 1, can you see from Q3 you have reached here? If you give 1, there are no next states. So that's why nothing is written here. But from Q0, if you get 1, you will reach to Q0 also, and you will reach to Q1 also. There are two chances if you give Q0 1. One is Q1, other one is again back to Q0. Okay. After that, next you have to give 0. So from Q1, if you give 0, you can see no output is there. So that's why I have written it this side. No output. Okay. But from Q0, if you give what? 0. From Q0, if you give 0, it is again taking you back to Q0. Okay. So from Q0, if you give 1, it is taking you, this is Q0. Previously 1 was taking you to Q1 and 1 was taking you to Q0. Next 0. Okay. Q1, 0, nowhere. Q0, 0, again Q0. Can you see here? From Q0, if you are giving 1, the previous one, this one is which one? This one, only one, this one. Okay. One is taking you to Q0 also and Q1 also. But from Q1, there is no other option if you give it 0. But from Q0, if you give 0, there are chances. From Q0, you will reach to Q0 also. And from Q0, if you give 0, you will again reach to Q3 also. So this is what this 0 is which 0? This one, the second last one. Okay, so you can reach to Q0 also and you can reach to Q3 also. The last one is that you have to get one more 0. Okay, so if this 0 you give to Q3, if you give this 0 to Q3, you will reach to final state, which is Q4. Okay, but if this 0 you give to Q0, if this 0 you give to Q0, there are two further states. Again Q0 and again Q3. Okay, so the final state is achieved by this final state. Okay, so I will send this PPT. So with this, I am about to end this class, and I will share PPT with you, and you should start doing it on your own and see what's the difference between deterministic and non-deterministic finite automata. And in case of non-deterministic finite automata, there are chances that it can again take you to the final state. Okay, so if there are chances that you start and you reach to the final state with some combination of inputs, it means it is accepted. Although there are other chances which are rejected, but if there is even one chance that it is taking you to the final state, it means that particular string is being accepted by your NDFA. Okay, so with this, I am going to end this class. So see you again. Till then, keep learning. Bye bye. Take care.